This is lecture 8 for week 9 of CS 1030. In this lecture segment, we're going to keep looking at circuits for adding binary numbers. So if you recall, in the previous lecture segment, we looked at building a half adder. Now we're going to extend that to building a full adder. So here's the circuit for a full adder. So the half adder had two inputs, A and B. So its truth table had to have 4 lines in it, or four rows in it, because 2 to the second power is 4. The full adder has a third input, an input carry in from the previous column. And so a 3-input circuit, of course, has to have 8 columns in it, or 8 rows in its truth table, because 2 to the third is 8. So the way it basically works is we're adding A and B, and then we also add in the carry in. So we're basically adding 3 binary digits, and we end up with sort of a complicated truth table. And doing some sort of a straightforward mapping from this truth table to a circuit is, as we said before, sort of beyond the scope of this class. So we're going to look at a different way to attack building a circuit that solves the problem that we have here. So let's start out by looking at a half adder. So here's a half adder circuit. It's exactly the same thing we looked at in the previous lecture segment. It adds 2 bits A and B, and it has the sum bit and the carry bit. And the thing that it doesn't do is take into account the carry. So, but what we want to do to deal with the carry from the previous column is we want to add a third bit to the 2 bits we already added. And the way we're going to do that is by adding a second half adder. So here's a second half adder circuit. This one takes as one of its inputs the sum of A plus B, which if you remember was computed by the exclusive OR gate. And as its other input, it takes the carry in from the previous column. So it's a completely separate input. It's the circuit that computed that carry in is not part of this full adder. Okay, so now it's just a half adder. So the sum is computed using an XOR, and this is going to be the final sum. And the carry is computed by an AND gate. And then the carry bits from the 2 half adders we're going to combine, and this might be sort of surprising, with an OR gate. So sort of naively speaking, what you might think of when you look at this is we'd need a third half adder to add the 2 carries out of the original addition and the second addition. And what I'm showing you is that we don't need that. We can just do this with an OR gate. And I want to try to explain to you why right now. So let's look at the case where this line is carrying a 1. So what are the conditions that make this wire carry a 1? Well, this line can only carry a 1 when both A and B were true, because that's the only condition under which an AND gate outputs a 1. Okay, so if this line is a 1, then the question is, what is this line? So this line has to be 0 in that case. So if A and B were 1, then exclusive OR computes 0. So now, when a 0 is fed into an AND gate, the AND gate basically sort of suppresses the other input. So if this input to the AND gate is 0, then the only possible output from the AND gate is 0. So what we can see here is that if this line is carrying a 1, this line has to be carrying a 0. And if we're just adding 2 things where only one of them can be 1 at any given time, we don't need the actual half adder to do it. We can do it with an OR gate. Okay, so what we've shown so far is that if this wire is 1, this one has to be 0. But we haven't shown the other part of what I said, that if this wire is 1, the other one is 0. So let's look at that. So what makes this line 1? Well, the output of an XOR gate is 1 only when its inputs are different. So if this wire is holding a 1, then A and B must be different. If A and B are different, that is to say, one of them holds a 1 and one holds a 0, then we know that an AND gate, in either case, regardless of which one is 1 and which one is 0, is going to output a 0. So the only circumstances under which this AND gate could produce a 1 force the other AND gate to produce a 0. And so again, we're not going to have this sort of awkward case where it was possible for both of these carry sums to be 1. So they can't both be 1 at the same time. So we don't need a third half adder here. We can just get the functionality that we want using an OR gate. And that's kind of sort of cool and clever. And what this sort of is an example of is looking at how a circuit works internally and coming up with sort of an optimized way to represent it using gates. And this is what the people building real computers do all the time. They have all sorts of little clever tricks like this that make everything work out. So this is kind of complicated. There's kind of a lot going on here. And so what I sort of would like you to do, if you don't mind taking the time, is after watching this, go back to the first slide and look at the truth table and just sort of convince yourself that this circuit implements the truth table. And you can do that again by just sort of reading off all 8 possibilities for the inputs and convincing yourself that the sum and the carry out for the full adder case are the correct things.